Hi, today I'll be reviewing AP Chemistry Unit 5, Kinetics. So let's get started. So 5.1, reaction rates. So kinetics is basically the study of the rates of chemical reactions, or how fast does a reaction react. And the reaction rate can be determined by stoichiometry, concentrations, temperature, surface area, catalyst, and many other factors. So what we have right here is a simple equation. And what we're going to do for basic kinetics is finding the rate of disappearance and the rate of appearance of this equation. So let's just draw a simple line graph where we have concentration as our y and time as our x-axis. Now, A is a reactant and B is a product. So A would basically be at top, while B and C would be at 0. And A would be lowering, while B and C are increasing. This is A. This is B. And green for C. And this is C. And in order to use an equation to calculate this, you could use the equation negative concentration of A over delta T will equal the rate of appearance of B and will equal 1/2 times the rate of appearance of C over delta T, or the change in temperature. And this equation can be modified in order for other chemical reactions. And you could basically use this in order to find the rate of disappearance and appearance without having to require a rate law. So clear all drawings and let's do 5.2. So the rate law is basically used as an experimental method in order to determine the rate of a reaction. And the rate law, so let's first go and explain all the variables. The rate is basically how fast the reaction is. The brackets for A and B, I'll change my color. So these basically denote concentration of reactant A and concentration of reactant B. K is the rate constant, and M and N are rate orders, reaction orders, my bad. And all of these work up to create the rate law. And this chart shows the overall reaction order from 0 to 3. There are more reaction orders, as you can see in the problem we'll do in a bit, and the general rate law for them. So just 1 second to just write it down if you want. And okay. So let's try a problem. So for a reaction 2A plus 2B makes C plus 2D, find the rate constant. So for this one, what you have to do is you first have to find, for concentration of A, one where A changes and the rate changes, but then the concentration of B does not. So trial 1 and 2 does this, with A changing from 0.1 to 0.2, 0.16 to 0.32, while B stays the same. So now you can basically, well, we also have to create the rate constant. So the rate would be rate equals K times A to the M, as we're trying to find it, and B to the end. So basically we are trying to find A. So you have concentration A a to the m equals, so you have 2 to the m equals 2, m equals 1. Now you have to do it for b also. And for b, we have to find two trials where a stays the same, but b changes. So for trials 2 and 3, we have a staying the same, but b decreasing by 2, while the rate decreases by 8. So b to the n equals, and now as 100 divided by 200 is 1/2, 1/2 to the n equals 0.04 divided by 0.32 is 1/8. So 1/2 cubed is 1/8, and that's basic algebra. So n equals 3. So the overall reaction order is 4th, and I'll just write it on over here. So Ka1 B3. Sorry for the bad 3. 1 sec. Just write it. Now you just have to plug in any of the trial data in order to find the rate constant K, which is what you're finally looking for. In order to do this, you have to do some algebra in order to separate the variables into just getting K from everything else. And I'll just figure some of the area up, and then you can do it. And so you have to divide both sides by a and b cubed. So the K will equal rate over concentration of A, concentration of B cubed. Now you can just put in one trial, for which I'll just do trial 1. So you have to do K equals 0.16 divided by 0.1. Sorry, my bad, not 0.1. 100 times 200 cubed. And now once you do this, you get K being 2 times 10 to the negative 10th, which is extremely small. And there you have it. That's basically your rate constant. And this can be applicable for all other trials with this equation. So I'll just erase everything and let's get on to 5.3. So the order of a reaction can be inferred by a graph. And basically what this gives is you have like a 0 order reaction, which is linear, and that's shown over here. The slope is negative K, and it's a concentration of A over time. The first order reaction will also be linear, and it'll have a downward slope with ln x over time. And that's the natural log of x, and that'll be over time. And then second order, that would be 1 over x, concentration of x versus time, and that'll be a positive slope with the slope equaling positive K. And along with this, you have the half-life. This is T 1/2, which will be 0.693 over K, the reaction, the rate constant. So if you have the rate constant, you can calculate half-life. And also with these equations, a to the 0 is basically the initial. And yeah, so, and t is time. Now let's do 5.4. So a reaction mechanism is basically a process in which a reaction occurs, and stoichiometry can determine the order of the rate law. We'll go more in depth into this after we go into collision model, and then we'll go into more depth. So 5.5, collision models. So for a reaction to occur, there has to be 3 main factors. The particles in the reaction must collide. they all must have proper orientation, and they must have sufficient EA, or activation energy. Temperature does not affect activation energy. However, temperature increases kinetic energy, which allows for more collisions to occur, which also increases the probability of successful collisions, along with increasing the ability for the collisions to have a sufficient activation energy. So temperature does not directly affect activation energy. However, it allows for a higher probability of these three requirements to occur because there's more particles moving, and with like the Maxwell-Boltzmann distribution curve, there'll be more particles being able to meet that EA barrier. And I'll be making the Unit 3 review also, so I'll go more in depth into the Maxwell-Boltzmann curve. And this picture over here shows collision between chlorine and a NaCl atom, and like it just shows an ineffective collision and an effective collision. So the ineffective collision has the collision not allowing the Cl from the NaCl to split, and it just has it stay the same. While after the collision, it allows the Cl2 to separate from the NO, making NO and Cl2. So that's why collisions are required in order to have proper orientation for being able to create new particles. So 5.6, reaction energy profiles. And this basically is like a introduction to thermochem, and you'll have like those graphs, like a enthalpy and endothermic and exothermic reactants. And I believe I made a video, like a short video on that in Instagram. So if you want, I believe it's on there. So enthalpy is basically energy that's released or absorbed in a reaction. And an exothermic reaction is basically in a graph when the reactant's energy is higher than the products. This is exo. And endothermic when the product energy is higher than the reactant. So this is endo. So decreasing the activation energy can increase the rate, as we talked about in the last unit. The activation energy has to be enough in order for reactions to occur. So decreasing the activation energy allows for more particles to be able to meet the barrier and the demand of EA. 5.7, reaction mechanisms. So a reaction mechanism is basically a series of elementary steps that are showing how like the particles collide. And an intermediate is formed in one step and consumed in another, and a catalyst is consumed in one step and formed in another. So let's try using this problem to determine which is a catalyst and which is a intermediate. So an intermediate is formed in the first step and then consumed in another step. And we can see that occurring with ClO. So ClO is formed from a reaction with chlorine and ozone molecules. So ClO is created, and then the ClO is then consumed with ozone in order to create Cl. Fluorine is found in the first step over here and is formed again in this step. So the chlorine is a catalyst, and the chloride. No wait, yeah, I think it's chloride. I'm not sure though. The ClO, that is basically that is consumed in that is formed in one step and consumed in another. So you have your intermediate as ClO and your catalyst as Cl. So 5.8, reaction mechanisms and rate law. So the rate of reaction can be no faster than the slowest step, and you can use stoichiometry coefficients in order to determine orders, which depend on actually you can't use stored coefficients to determine orders, and that depends on actual collisions. However, you can use coefficients from the elementary steps in order to determine them. You can't use it for anything else. You can only use elementary reactions in order to determine the stored coefficient. So let's try getting the let's try finding the rate law for this reaction. So what you have is you have NO and Br2 makes NO-Br2 for the fast step. And you have this as the slow step. So as you have NO and Br2 makes NO-Br2, you can just take out the NO-Br2. And you just have NO plus Br2 plus NO makes 2 NO-Br. So the rate law would be rate KNO squared and Br. So that's pretty much it. So let's go on to 5.9. So 5.9, steady state approximation. So for what you have to do for this one is basically it just talks about equilibrium, which also is in later. So equilibrium is basically when some reactions are reversible, and there's like a symbol for that denotes it, which is basically like this. And that just denotes that the reaction is reversible. And the observed rate constant is K. And also along with that, rate orders can be weird, like half order, which is not seen too much, but is still there. I'm not sure you'll be testing on it, but it doesn't hurt. Stay safe. So this one talks about multi-step reaction energy profiles, which basically there's not much to cover for this one. It's basically the highest activation energy is the slowest reaction, and it's a slow step. So when you have the highest EA, you have the slowest reaction, and that reaction determines rate constant. And for example, this one has the highest EA because it has the highest curve, and the others are fast steps. And the last one. So catalysts. So catalysts basically increase the rate by forming more stable complexes, increasing collision frequency, and improving orientation. Homogeneous catalysts have the same phase as all other catalysts, and the catalysts make the reaction faster, not the reaction steps. And basically how a catalyst works is, so when you have like a graph of, let's say, let's make this a graph of the energy required. So what catalysts do, so I'll draw this in white, they basically lower the EA barrier through things like this, which basically allow more particles to have the energy required and have, like, it basically increases the probability of more collisions by doing it, which I talked about in 5.6. So clear all drawings. So I guess that's it. So thank you very much. And it's kind of late right now. So yeah, so thank you. I hope you have good luck with studying and stay safe.